Today we're going to talk about Maxwell's equations. They're named after him and he did a lot to organize them, but he didn't do everything. The main thing he did was notice that something in Ampere's law was not quite right. There's something missing. If you remember, the way we used it was if we did the line integral of the magnetic field around a closed path, that would be equal to the current going through the surface bounded by that path. So if we want to see what that looks like, we can imagine we have a parallel plate capacitor. These two gray discs are the plates of the capacitor. And we want to measure the magnetic field here, some distance r from the wire that's carrying the current that charges the capacitor. It would be reasonable to assume that the surface through which the current travels is this disc that exactly fits the circle. But there's nothing that makes us choose that shape. What if instead of this shape, we decided to put a balloon around one of these plates, stretch the mouth of it over the plate so that we have something like this below. This looks more like a cylinder than a real balloon because that's what I can draw in Word. But if we do that, now you notice there is no flow of positive charges through this balloon. They all get stuck on the plate, which is inside the balloon. This means if there is no current going through this surface, then the integral of j dot dA would be 0. And if that's 0, then this integral of b dot dl is 0. Since we know the path length itself is not 0, that tells us there's no magnetic field. Now remember, that's around this red dotted line. This is telling us there is no magnetic field around this path. However, if we instead chose the simpler surface, we would see that yes, there is a magnetic field as long as the capacitor is charging up and we have a current flowing. Now, the yellow surface, which one we pick, is imaginary. The physics can't depend on that. So we obviously have a problem here between these two results with two different imaginary surfaces. And what Maxwell figured out is there must be something that takes the place of the regular current flow in this case to produce the same magnetic field. And what he called that is the displacement current. And we can define that displacement current density as this epsilon naught that's popped up all over the place times the time rate of change of the E field. If we want to talk about the current itself instead of the current density, we could say it's epsilon naught times d phi electric dt. So the change in the electric flux. Now we write Ampere's law in a different way. Integral of b dot dl is the sum of these two current densities, or the sum of these two currents, multiplied by mu naught. And what we notice is if current is flowing through the wire and charging the capacitor, not only do we have a magnetic field from the regular current here, but we would also get a magnetic field not from the regular current, but from the displacement current here, if we're using this shape instead of the disk. And it turns out that you get exactly the same answer. This is just what it takes to patch up Ampere's law so that it doesn't matter which surface you choose, which we know has to be the case. So this is our final form of Ampere's law, where we have these two terms on the right and the line integral of b dot dl on the left. When we put that together, now we have all four of Maxwell's equations. This is the guts of electricity and magnetism and the second semester of the course. We have first Gauss's law, which says if we do the integral of the E field through the area of a shape that is closed, we get the charge enclosed divided by epsilon naught. This is Gauss's law, which we've used before. If we look at Gauss's law for magnetism, we discuss the fact that we don't really do anything with this because we can't draw a surface that gives us a different number of positive and, or rather a different number of north and south poles. So this will always be equal to 0, and this is true, and it means there are no magnetic monopoles, but it's not particularly useful for solving problems. Then we have Faraday's law, which tells us the E field going around a closed loop is equal to the negative of the time derivative of the magnetic flux. We've used this before. Notice that if we were in electrostatics where we had no magnetic fields, much less changing magnetic fields, this term would be 0, And what we get here would be Kirchhoff's loop rule. The sum of the electric field times the distance, that gives us the voltage jumps around a closed path, would have to be 0 since we wouldn't have this term. And finally, we have the new Ampere's law as repaired by Maxwell. What you should notice is there are some similarities and some differences in these things. E and B are, these two expressions are very similar. We have the same thing on the left above for E as we do on the left below for B. The only difference, again, is what's on the right. If we had magnetic charges, if someone discovers magnetic monopoles, then we'll have a term here, something like mu naught times whatever we decide to use for magnetic monopole number. Down here, we have this line integral of E around a closed loop, and we get it proportional to time derivative of magnetic field flux. On the other hand, if we integrate B around that closed loop, we get a term that's proportional to the time derivative of the electric field flux. Now, you notice we have these universal constants here that we don't have up here in Faraday's law. That's just because of our choice of units. So that's not really a significant difference. In that sense, this is the same as this part of Ampere's law. This is the part that we don't have in Faraday's law, and again, the reason is we don't have a collection of magnetic charges moving along a line giving us a magnetic current. We could write this in differential form instead of integral form, and if you had already had vector calculus, that's what we do because it's much easier and you can find some really interesting results that way, but that's not a requirement for this course. I can still show you what these equations look like in differential form, though. What we would get is what's called the divergence of E. In other words, E comes out from or goes into a point depending on density of the electric charge divided by epsilon naught. For B, we get that B does not ever come from a point or sink into a point because we don't have magnetic isolated single charges. The curl of E, which is how E rotates around, is equal to time derivative of B, and the curl of B is equal to this regular current density plus this time derivative of E. You can think of this as being lines of B curl around both regular currents and displacement currents. Lines of E can curl around changing magnetic fields. These are much smaller, and if we knew some vector calculus, we could use some identities and move from these four. We could take these four equations and we could get a wave equation for B and a wave equation for E, which tells us how those fields would travel through space, and that's what we'll do next.